So I'm going to start with a brief introduction to the GaN transistor. I'll then look at the basic GaN design approach, looking at a single stage transistor. Now, obviously it's quite an in-depth subject. There's a limit to what I can cover in an hour. In half an hour. I won't be keeping you an hour. I'll then move on to thermal considerations, very important. And I'm going to then illustrate this with 3 different GaN PA design examples using 3 different commercially available GaN foundries. There'll be a 15 gigahertz PA for line of sight links. This uses Cree's quarter micron process. Then a 2 to 18 gigahertz non-uniform distributed power amplifier using Triquint's process. And finally, a 25 watt X-band PA for radar applications using WIN's quarter micron process. So all quite different requirements with different approaches. But there are a lot of basic underlying similarities. I'll then end with some conclusions and summary. Now, gallium nitride is a wide band gap material, band gap of 3.4 electron volts compared to 1.4 electron volts for gas. What this boils down to is you have a much higher breakdown voltage, which means you'll be able to get more power out for a given size of transistor. Pretty much all commercially available quarter micron GaN processes have a source coupled field plate. That's that. It's a little shield that goes over the gate. And what this does is it reduces the fields at the surface of the drain gate voltages, and so it increases the breakdown voltage of the transistor. Now, at higher frequencies, when people want to operate to higher frequencies, they sometimes dispense with this field plate, because what this field plate does is it increases the gate source capacitance. So if people remove the source coupled field plate, they sometimes include what they call a gate field plate, and they shape this gate here to provide that shielding. These are the DC characteristics of a Cree quarter micron GaN transistor. And one of the things you'll notice is quite a high knee voltage, about 5 volts, compared to what you might be used to with a gas FET. And indeed, these transistors tend not to have much gain below about 10 volts VDS. You can see these very negative slopes here. This is a thermal effect. So how do GaN PAs differ from gas PAs? Well, the operating voltages are quite a bit different. Typically 20 to 40 volts for GaN compared to 4 volts to 12 volts for gas. The power densities, the output power per millimeter of gate width, are much higher for GaN. The supply currents can be higher. The thermal conductivity of the silicon carbide substrate, and all of these processes that I'm going to show you examples on have a silicon carbide substrate. That's much higher than for gas. The allowable channel temperature of the transistors for reliable operation is a lot higher. And together, these features mean that GaN MMICs can be used to realize high power amplifiers with a much higher output power than you can with gallium arsenide. So one of the first steps with a simple GaN PA design is to select your device and the bias. Now, larger transistors with more total unit gate width will have a higher output capability. However, at higher frequencies, the gain degrades as the transistor sizes increase. That's both the number of fingers and the unit gate width. You must make sure you've got adequate gain across your band of interest. And you need to make sure that your thermal performance is adequate. I'll keep coming back to this, but you know, it is your responsibility as the designer. And this is affected by the transistor size and the bias. More on this later. Now, for a quarter micron GaN silicon carbide process, 28 volt VDS and 100 milliamps per millimeter is typical bias. The GaN transistors are biased in class AB, and they can go into quite deep AB and still have a reasonable amount of gain. As you back them off in the bias, you find the gain reduces and you sacrifice some gain. You win a little bit of efficiency. The saturated output power capability is largely unchanged. So this shows you what happens with unit gate width. This is the frequency, this is G max, and for those familiar, you'll see this breakpoint here. Below this breakpoint, we're in a region of conditional stability. It's possible to make that amplifier unstable by selecting the wrong passive loads at input and output. Above here, this is unconditional stability. So this is really a figure of merit. This is actually the maximum stable gain. And what you see here is that the wider the unit gate width, the less gain you have. At lower frequencies here, this doesn't matter so much. And we see a similar effect with the number of fingers. As you increase the number of fingers, the device gets physically wider, parasitic effects increase, and at the higher frequencies, you sacrifice some gain. So the first example we're going to look at is a 4-watt X-band PA. Now, this used to be quite a tricky thing to design, but in honesty, if you've got a good GaN process, this is not a difficult design to do anymore. We're using on this first example, Cree's quarter micron GaN on silicon carbide process. We've selected an 8x120 micron device biased at 28 volts VDS and 100 milliamps per millimeter. And we've plotted here the G max, and what you can see is we've got really a ton of gain for one device, 18 dB. And to be honest with you, the source coupled field plate helps with this because it reduces the capacitive feedback from the drain to the gate. So you get a lot of gain from a single device. We are in a region of potential instability or conditional stability. So the first thing we do is we add some resistance at the input, of course. We don't want to throw away the power. And we add some resistance to stabilize our transistor within band. Now you start trying to take a transistor, which is only conditionally stable, and then start trying to design an amplifier by matching the input and the output, you'll run into all sorts of trouble. So we add some resistance, and you can add series, and you can add shunt. We've added a bit of both. If you put 1.5 ohm series here, make sure the resistor can handle the RF current going through it. Then you see at 10 gigahertz, we're now unconditionally stable. We add a 16 ohm in shunt, and you see we're now stable to quite low frequencies. This is possibly a little overkill, but we're not going to leave all this resistance in all the way through the design. As we add our matching networks and our biasing networks, we'll introduce some unavoidable losses, and we'll be able to reduce these resistors and possibly remove one of them. Here you see this is now stable down to really quite low frequencies. Now, this resistance we add at this stage is just there to stabilize it in band with a little bit of guard band. Ensuring the low frequency stability in particular, where these transistors have tons of gain, is a vital part of the design process, but it's something we can do later. Similarly, we need to ensure that we have unconditional stability of the complete amplifier to the maximum frequency at which this transistor has some gain. We now go to our load pull bench in our simulator. This blue contour here is the input impedance, and it's 4 ohms plus minus J 3.57, so low resistance capacitance, as you might expect. Now, for a 4-watt gas device, this would be much closer to the short circuit point here. It's a relatively low impedance still. What the simulator does, we present all these different load impedances here, and we measure the power and the PAE and the gain, or rather the simulator does. And from this, we can plot the load contours that Steve spoke about earlier. And I'll show some of these later for some of the other examples. What we have here at the 4 dB compression point, and to be honest with you, for the GaN transistors, if you really want to get the most out of them in terms of power and PAE, you need to drive them a little way into compression. We're seeing 36.3 dBm of output power and 49% PAE. Now, we can then go on and look at the harmonics and look at optimizing the impedances at the harmonics. And in honesty, we seldom go beyond the 3rd harmonic when we're considering this. And how much use this is entirely dependent on how accurate the model is. This is a schematic. We just put this example together for illustrative purposes for this talk. So we never went beyond the schematic stage. You can see we've got a low pass structure on the output. We've got our drain bias here, a low pass structure on the input to take that low impedance up to our 50 ohm point over here. And this capacitance here presents a good short circuit in band. We apply VDD here. Similarly, at the input here, we apply a gate bias here. This resistance and capacitance there, that's for ensuring lower frequency stability. It's not there to affect our in-band performance. And this is what we achieve. We have a good input return loss across our band of interest, across the whole of X-band, pretty much. Actually, sorry, not quite the whole of X-band, but from 10 to 12 gigahertz. We have a negative gain slope, which is what happens if you reactively match a single stage. If you want a single stage amplifier to have a flat gain versus frequency response, you need to introduce some lossy matching at the input with a power amplifier to facilitate that. With a multi-stage amplifier, you can introduce some tailoring of the gain response into stage. Here are your various stability metrics over here, and you can see from DC to 20 gigahertz there, we're unconditionally stable. Looking now at the large signal performance, we achieve 36 dBm from 10 to 11.6 gigahertz there. This shows how the current varies. You can see here when we're in small signal, the current is our quiescent current. As we ramp up the power, the current goes up. You need to make sure that your amplifier can cope with the currents here when it's operated in saturated conditions. And you can see also the PAE varies, and we get a peak PAE here of about 45%. So, thermal considerations. GaN transistors can operate reliably with a much higher channel temperature than gas. For a gas transistor, you're looking at 125 to 175, depending on your appetite for lifetime. With a GaN transistor, 225 to 275 is the sort of range. However, GaN transistors also operate at a much higher power density, so good thermal design is still essential. This is the so-called Arrhenius plot, and all foundries produce these when they develop a GaN process. And what they do is they bias the transistor up to operate at a really high junction temperature here. And they do that so that they can have some failures in a reasonable lifetime. They then draw this line through so they can work out what sort of lifetimes they can expect at sensible junction temperatures. And so you can see here, at 225, we get 2.6 e to the 7 hours. So that is about 3,000 years. So if the Emperor Nero had have biased one of these transistors at the start of his reign at 225, when we get to this point now, it's still 1,000 years till we start reaching the median time to failures. A little bit more on thermal. It's the designer's responsibility to ensure that the transistors are operating at a low enough junction temperature to provide adequate reliability. Channel temperature is affected by the substrate thickness. This tends to be fixed, typically 100 microns. Device layout. when you get a PDK for the process, you have a set of transistors with a given layout. These are the transistors that have been modeled. You can develop your own transistors. You can adjust the layouts to spread the fingers. Not all foundries like this. However, you then need to think about modeling those transistors to accurately predict the performance. The ambient/base plate temperature and the total power dissipated in the device, these are two things that you have control of. So what this is showing you is that thermal conductivity of silicon carbide is very good. This is the left-hand scale here and the blue trace here. And what you can see is it's 10 times as good as gas. Indeed, at room temperature, the thermal conductivity of silicon carbide is higher than gold. However, the thermal conductivity drops as temperature increases, and quite significantly, from about 4.2 here at room temperature down to about 1.7 here at 200 degrees. And this really complicates the thermal design process. It also means that the thermal impedance of GaN transistors and MMICs is temperature dependent. This is some commercially available data for packaged Cree GaN transistors. And what you can see is that the thermal impedance depends on how much power you're dissipating. So this is the next example we're going to look at. This is a 15 gigahertz PA for line of sight links. Cree's quarter micron GaN process. We're optimizing for IP3. We're going to put a complex modulated spectrum through this. So we need to ensure that we preserve modulation fidelity. This is the specification we started out with. This is the 15 gigahertz point-to-point link band. We want more than 20 dB of gain, an output IP3 of 45 dBm at plus 22 per tone, 38 dBm PSAT, PAE of 35%, and the chip area, we want it to be a lot less than commercially available gas parts doing the same. And the reason for this is the GaN processes are more expensive on a unit area basis, but the power density of GaN is higher, so you should be able to create a PA with similar power capabilities that is much smaller. So this is a 4x250 micron transistor, and on the Cree's quarter micron process at 15 gigahertz, this is capable of about 4 watts per millimeter of output power. You can see the intersource vias here. Some of the other examples I'll be showing have vias at the edge, but all foundries are now moving towards this intersource via approach. So that's vias through substrate vias connecting the front side to the back side, providing you a very low inductance ground connections. They're all moving that way. One of the ancillary benefits, it spreads these fingers here. It does introduce some more parasitics, but it spreads the fingers, improves the thermal performance. The PDK that we had in this instance is able to account for the thermal effects on RF performance. You do have to say what the thermal impedance is. That's something, the onus is on you to do that. You say what the thermal impedance is of the transistor. You bias it as you wish, and the PDK will work out the impact on the RF performance. So we're looking at this 4x250 micron device, and we're going to use 2 of these to generate the sort of power that we want for this 15 gigahertz PA. This is the Gmax, and this device is unconditionally stable above 12.5 gigahertz, which is nice for our 15 gigahertz design. We have a Gmax of about 14 dB at 15 gigahertz. So we're estimating 11, 12 dB per stage. So we're going to do a 2-stage design. And the reason we don't achieve the 14 dB is the implementation losses, the match in the biasing circuitry, gain flattening, which we're going to do interstage, and low frequency stabilization to make sure that this massive amount of gain you've got at low frequencies doesn't cause us any problems. So looking now, this is just a small signal, S parameters, and this is the S22 here at 15 gigahertz. And you can see that it's not an awful impedance. And by adding a 0.3 nanohenry shunt inductor, that transforms around pretty much to 50 ohms. This is one of the benefits of GaN. For a given output power, the output impedance is higher than on a process with a much lower breakdown voltage. And that means that you can have a simpler matching structure, or it's easier to have a broadband match. So we then did some load pull simulations, and these are the load pull contours. And indeed, they aren't circles, they are elliptical shapes. And this one, this Smith chart is the load pull contours for maximum power to the load. These are the load pull contours for maximum PAE, and these are the load pull contours for best linearity. So here, this point here is the optimum PSAT, and that turns out to be round about 50 ohms in parallel with 0.3 nanohenries. And we step up, I think these are half dB steps as we step out here. So you see, to get within 1 dB, it's a relatively small area. Then the optimum PAE was 46.8%, just looking at the fundamental tuning. And here we need 70 ohms in parallel with 0.3 nanohenries, and optimum linearity was 140 ohms in parallel with 0.3 nanohenries. So as the designer, you need to choose the compromise point. You can't simultaneously optimize for all of these parameters. And this is what we ultimately came up with. There's an RF input here, ground signal ground, RF output here, ground signal ground, and 2 transistors in the output. This is the shunt inductor that gives us the shunt 0.3 nanohenries, and in this instance is essentially tuning out the output capacitance of this transistor. Then we have some low pass matching. You can see here we've got 2 shunt capacitors going down to ground. On the input here, we have a meandered line for the gate bias. Then we have a decoupling capacitor. Then we come through a series resistance, not too much series resistance, because when you drive these hard, the leakage current is not 0. Then this is where we apply the gate voltage. We then have some RC decoupling here, and that's there to improve the low frequency stability down to very low RF frequencies. Anything you want to do at even lower frequencies, you can do off chip. You can see here we have decoupling here, a different shape. We just had some more space, so we put in a different shape decoupling capacitor, fill the area. It's expensive per unit area, so we make use of it. This is a parallel RC, and that's quite a nice way of improving stability. What this does is it presents more loss at the lower frequencies where the C is a higher reactance. And we have a similar parallel RC here. And the input stage, it's actually the same size of each of the output stages. Now, if you were just interested in PSAT, you could have made this smaller and got better efficiency from the complete amplifier. Because we're interested in linearity, we want to make sure that this stage, this input driver stage, is not started to compress at the same time as these output stages. And this is a comparison to this is the size of a commercially available gas amplifier that does a similar performance. It's not actually quite as high linearity, but it's pretty close. And what you can see is we're able to make a much smaller part and achieve the same sort of linearity performance, same sort of output power. This is the simulated performance. We've got flat gain across frequency, around about 22 dB of gain, a nice input match, better than 17 dB. The output match degrades towards the top of the band, and that's because we're matching for linearity rather than conjugate. This is the final performance at 3 dB compression. When you look at GaN PAs, MMICs that are commercially available, you'll see that the output power is quoted at a wide range of compression levels. The highest I've seen is 10 dB. So so they could say it's a 10 watt amplifier, and when you look at the data sheet, it's 10 dB compressed. We think that's a little bit over the top. I think sort of 3 to 6 dB is reasonable, 10 dB. This is the output IP3, and it's around about 46 dBm, which is what we were looking for. So this is just a summary of our target compared to the simulated, and you won't be surprised to see that all of those surpass all of those. Now, I mentioned that this is for line of sight links. So what we want to do is to put high order modulation through it. Now, I've just got this one slide on this. If anyone is interested in more information, if you go to the Pletech RFI website, there's a white paper on this, and there's a video tutorial on there. But what you can see here is this green is the spectral mask. This is the spectrum of the signal once it's passed through our amplifier. So what you do is you put your modulation through a root raised cosine filter, and it's only going to work at the sampling instance. This ISI here and here, that's caused by the root raised cosine filtering, which you had to put in to get the modulation sidebands down. It's all quite involved to go into in detail. There is more information on our website for those who are interested. So next example is a non-uniform distributed power amplifier. And this was on Corvo, knee triquint, which it really starts to get quite challenging. 10 dB of small signal gain, 7 watts out, 25% efficiency. You always need to sacrifice a degree of PAE when you operate over wider bands. And again, that's at 3 dB compression. So the non-uniform distributed power amplifier we chose, 10 devices, and you taper the characteristic of the drain line so that each device is operating to a near optimum load impedance. And for this process, it was about 100 ohms per millimeter of gate width. Class AB bias, 30 volt operation. Now, generally, the drain line gets narrower as you move away from the output. The device furthest from the output than the others is made larger so that the drain line is still a vaguely sensible width, hence non-uniform. And we introduce series MIM capacitors on each of the gates. And what this does is it allows us to use slightly larger transistors for the same upper cutoff frequency, which increases the output power at the expense of gain. Like all things in design, it's a trade-off. And we can vary the values of those capacitors in order to ensure a similar drive level at each device. Here's the circuit schematic. Now, it looks pretty simple, but honestly, it's quite difficult to get it all right. And we've got these 10 transistors. This is the big one over here. This is the RF output over here. This transmission line gets narrower, narrower, narrower all the way over here. This is the input here. And this input, it's a low-pass filter. So these are the series elements, the series inductors, a termination load here. And these transistors are the shunt elements. So as you make these transistors bigger, the shunt capacitance get larger, the cutoff frequency gets lower. So by adding a series capacitance here, the input capacitance here is, the effective input capacitance here is reduced. So you can use a bigger transistor for the same cutoff frequency, but you throw away a bit of gain. Of course, we need these resistances here to get some gate bias in. And this is what it looks like. The output's over here. This is the drain line, getting narrower and narrower. You can see it really is very narrow here. This is the larger device here. This is the gate line. That open circuit stub is just a little bit of shunt capacitance, a very modest amount of shunt capacitance. Another thing that's really tricky actually is designing this inductor. You need it to be wide enough to carry the current. You can see the underpass is really wide because that's got less current carrying capability. And it needs to be big enough that it has adequate reactance at the low end of the band, 2 gigahertz, but it also needs to behave sensibly at the top of the band at 18 gigahertz. And this is what it looks like. So you see really quite a nice flat performance all the way up to 18 gigahertz. Very nice input and output return losses. And the output power, round about 38.5 dBm, a little bit more here. That's 7 watts. And the PAE, round about the 25%. Okay, I'll whiz through the last one. This is the an X-band PA on WINS process, 10 to 12 gigahertz, 25 watts. So same design approach as before. We select the device size. We've gone for an 8 by 120, and we can see this is unconditionally stable round about X-band. And this is an effect that you often see on these larger devices, particularly the ones with edge-coupled source vias. We return back to a region of conditional stability here. So we did load pull, and we discovered that we could get 36.3 dBm with 45% efficiency, so we need 8 of these devices. We start with a single one-cell design, and we simulate and optimize the performance. And from this simple single cell, we're seeing around about 15 dB. We found we had to, with this process, we had to push a little bit further into compression to get the sort of useful performance we're wanting. This is at 6 dB compression, 36 dBm out. This is a topology we went for. All big PAs, MMICs, have this sort of topology. Large number of parallel devices at the output, driven by a smaller number of parallel devices. And this is the performance we achieved for the final amplifier. Greater than 25 dB of gain, slight positive slope. Across this sort of 10 to 11.5, we're achieving round about 32% efficiency and a P out of 25 watts. And that's what the layout looks like. So you see these balancing resistors. These are very important. If anyone's going to design one of these, do include some balancing resistors. Otherwise, you can run into horrendous problems of loop instability. And things can look fine here and here, but inside you can get problems. So to summarize and conclude, GaN MMIC technology is very well suited to the realization of microwave PAs. Don't think that's particularly controversial. There are a number of GaN processes that are now commercially available. We've shown examples of 3 MMIC designs that we did at Plextech RFI. There was a 15 gigahertz PA for line of sight links on Cree's process, a 2 to 18 gigahertz non-uniform distributed PA on Triquints/Corvo's process, and a 25 watt X-band PA on WINS process. Don't forget to consider thermal performance. Sorry if I've banged on about that, but you'll thank me for it at the end of the day. That's all. Thanks.
Yes. The comparison of size where you showed the GaN device and the gas device.
Yeah.
What's the cost delta between the two? Account for the size difference.
It varies all the time, and it depends which process you use, but it's roughly 2 to 1. Yeah, you know, for a foundry that has both, it's round about the 2 to 1. But
account for the area difference, or is that
no, 2 to 1 per unit area, roughly, very roughly. But then there are some foundries who have more expensive processes, and some foundries who don't. It depends on the volume you've got to run and everything. But if you start on a working metric of 2 to 1, that's a reasonable starting point.
And have you looked at other substrates than silicon carbide? And then you can get them on cheaper substrates as well?
Yeah, absolutely. So we don't develop the processes, we just do the design. But people like Macom, for example, they have both silicon, they have GaN on silicon and GaN on silicon carbide. And your performance does suffer. You get less output power per millimeter of gate width with silicon. It just isn't as good thermally. However, it will be cheaper. So you have to weigh up your performance compared to your cost, and for each different application results in a different choice. If you can get MACOM to tell you which they've used for which, that'll give you some good insight into where the choice cuts off.